This week we'll be covering Chapter 5, Identifying Good Measurement. We'll look at some examples of what good measurement looks like and how to go about identifying and testing different measurement techniques. More specifically, in this chapter, we'll go over some different ways to measure variables and talk about how some methods are more sound than others. We'll also talk about the idea of measurement reliability and look at whether the scores that are observed are consistent. We'll also talk about the validity of measurement. So is what we're intending to measure what we're actually measuring? Finally, we'll talk a bit more about construct validity and discuss in more detail the validity of its evidence. So let's start off by talking about some different ways in which we can measure variables. If you'll recall from Chapter 3, any variable can be expressed in two ways, either as a conceptual variable, which can exist at either a construct or a theoretical level, and as an operational variable, or specifically, how the variable will be measured or manipulated. When we talk about measuring variables, several important decisions need to be made. The first one is how a variable should be operationalized, or how we're going to specifically measure a conceptual variable. Let's take the example of happiness. How can we operationalize happiness? Well, a psychologist named Ed Denier at the University of Illinois, he's also known as Dr. Happiness, has spent most of his career studying happiness. He started by creating a conceptual definition of what happiness is, which he called subjective well-being, or a person's own perception of his or her well-being. Then Denier and his colleagues came up with an operational definition by asking participants to respond to 5 items about their life satisfaction on a 7-point scale, where 1 corresponded to strongly disagree and 7 corresponded to strongly agree. While this is one way of operationalizing subjective well-being, there are other ways that it can be done as well. In order to study conceptual variables other than happiness, you would follow a similar procedure. First, define your construct, or the conceptual variable, and second, create an operational definition for your construct. You can see here in Table 5.1 some examples of how a variable can be operationally defined in multiple ways using this method. We saw on the previous slide in Table 5.1 that operationalizing a variable can occur in different types of measures. The 3 common types of measures that are used in psychological research are the self-report measure, the observational measure, and the physiological measure. The first one is the self-reported measures. They operationalize a variable by recording people's answers to questions about themselves in a questionnaire or interview. For example, operationalizing caffeine consumption by asking, how many caffeinated beverages have you consumed today? Observational measures, or behavioral measures, operationalize a variable by recording observable behaviors. For example, operationalizing allergies by observing how often someone sneezes, or using physical traces of behavior, like operationalizing cleanliness by quantifying how much dust someone has on their furniture. Lastly, physiological measures operationalize a variable by recording biological data, such as brain activity, hormonal levels, or heart rate. For example, operationalizing whether someone can distinguish between 2 different speech sounds by examining his or her brain responses to those different speech sounds. So which operationalization is best? Well, a single construct can be operationalized in all 3 ways, and one is not necessarily better than the other. However, it is preferable that the 3 types of measures show similar patterns of results. If you were to get different results from each method of measuring the same variable, then you couldn't accurately say that they were both measuring the same thing. So when we operationalize a variable through a scale or survey, we need to make sure that we're thinking of what types of scale we're going to use. While all variables must have at least 2 levels to allow for change, so they can vary, the levels of operational variables can be coded using different scales of measurement. The primary distinction is between categorical variables and quantitative variables. Categorical variables, also known as nominal variables, have qualitatively distinct categories or levels. For example, the variable pets, such as cats, dogs, or fish, or the variable color, maybe red, blue, or green. These levels of each variable are simply categorical. They don't relate to one another in a hierarchical fashion. There's no particular order to them. Quantitative variables, on the other hand, are coded with meaningful numbers. for example height, weight, or scale of subjective well-being. There's some inherent value to the levels of the variables that relate them to one another. There are three subtypes of quantitative variables. The first are ordinal scale variables. These are simply related by a ranked order, first, second, third, maybe the places in a race. First place isn't necessarily twice as fast as second place, but it is higher in the order. The second are interval scale variables. Numerals represent equal distances between levels, and there is not a true 0 point. 0 does not simply mean nothing. For example, IQ score. A score of 160 is twice as large as a score of 80, but here there is no true 0 point, so the values are simply grounded relative to one another. Finally, we have the ratio scale. Here, numerals represent equal intervals from one another, and there is a true 0. For example, height or exam scores. Alright, so next I'm going to cover measurement reliability. We're going to talk about the three different types of reliability, how we can use scatterplots to quantify reliability, how we can also use the correlation coefficient R to evaluate reliability, and finally, how we interpret reliability when reading about it in journal articles. There are three types of reliability when it comes to measurement. The first is test-retest reliability. This is where you find consistent scores every time the measure is used. For example, if you were to give an IQ test at one point in time, T1, say at the beginning of a semester, and again at a second point in time, T2, at the end of the semester, the score should be relatively consistent across the two times. Interrater reliability is when you find consistent scores no matter who does the measuring. For example, two observers measure how often a child smiles during 1 hour at a daycare playground. To determine the interrater reliability of the measurement, you would see if their counts are consistent with one another. Internal reliability, also known as internal consistency, is when a participant provides a consistent pattern of responses regardless of how the researcher has phrased the question. For example, let's say a researcher asks, in several different ways, how lonely you feel. If there is internal reliability, your responses will be consistent with one another across all the different ways you were asked. There are two ways in which researchers can evaluate reliability. One is by using a scatter plot, and the other is by using the correlation coefficient R. Let's look at this example. It used to be thought that smarter people had bigger heads. Thus, head circumference, or size, was an operationalization of intelligence. One way you could determine if this measure is reliable is by using test-retest reliability. You could measure each participant's head twice and see if the results were similar. This slide shows you a data table for the 4 participants and the scatter plot of that data that were used to do exactly this. Evaluate the test-retest reliability of this measure. The first head circumference measurement is on the y-axis, and the second measurement is on the x-axis, with each dot representing one of the 4 participants. Given that head circumference doesn't change, we would expect that the two measurements should be similar, as indicated by how close the dots are to the slope line. Should that be the case, we would be able to say that the test has a high degree of test-retest reliability, which you can see here that it does. It's important to point out here, however, that this measure of reliability doesn't necessarily mean the measure was a good way to operationalize intelligence, just that it has strong test-retest reliability. We can also use scatterplots to examine interrater reliability. Let's look at this next example. There are 2 independent observers, Mark and Matt. They are each tasked with rating 10 young children on a scale from 1 to 10, indicating how happy they each are. In order to see how well their ratings agree, we can make a scatter plot with Mark's ratings on the x-axis and Matt's on the y-axis. You see that Mark and Matt have high interrater reliability, indicated by the dots being close to the slope line in the graph on the left. However, Mark and Peter do not have high interrater reliability, since the dots indicating each of their ratings are farther spread out from the slope line in the graph on the right. Although scatterplots are a good first step in evaluating reliability, a more common and more efficient way is to use the correlation coefficient R. The correlation coefficient, or R, is a single number that describes how close the dots on a scatterplot are to the line drawn through them. Notice that the direction of the slope is different in the 4 scatterplots shown here. A and B show an upward slope from left to right, which is a positive slope. C shows a downward slope or negative slope, and D does not slope either up or down, indicating a zero slope. The spread of the dots in a scatter plot correspond to the strength of the relationship. When dots are close to the line, as in graph B, you have a strong relationship. When dots are spread out, like in graphs A or D, you have a weak relationship. When your slope is positive, R is positive. When your slope is negative, R is negative. The value of R can range from -1 to +1, and the stronger the relationship, the closer R is to that -1 or +1 endpoint. The weaker the relationship, the closer R is to 0. An R of +1 is the strongest positive relationship, and an R of -1 is the strongest negative relationship, whereas an R of 0 or close to 0 is no relationship at all. How do you think psychologists use the strength and direction of R to evaluate reliability? Well, let's talk about each type of reliability here. For test-retest reliability, remember we measure the same participants at least twice, time 1 and time 2, and then we would compute R. If R is strong and positive, 0.5 or above, then you have a good test-retest reliability score. If R is positive but weak, it's a sign of low test-retest reliability. Note that test-retest reliability is only relevant for variables that do not change over time. It wouldn't be relevant for something like an organism's weight that is expected to change over time. For interrater reliability, here two observers rate the same participants at the same time, and then an R is computed. If R is positive and strong, 0.7 or higher, you have good interrater reliability. If R is positive but weak, you do not have good interrater reliability. A negative R would mean terrible interrater reliability because raters are responding in opposite directions. Internal reliability is relevant for measures that use more than one item to tap into the same construct. A set of items has internal reliability if its items correlate strongly with one another. In that case, you can average across those items to get a single overall score for each participant. Researchers typically will run a correlation-based statistic called Cronbach's alpha, or coefficient alpha, to see if their measurement scales have internal reliability. First, they collect data on the scale from a large sample of participants, and then they compute all possible correlations among each of the items. They then use those correlations to compute one number known as Cronbach's alpha, which is similar to R, but involves the relationship between all the scale question responses. The closer that number is to +1, the stronger the internal reliability of the survey. Sometimes review articles will present the values of the measured reliability coefficients, either as an R value or an alpha value, and we can see an example of this here. You should now be able to understand a little bit what these numbers mean in the table. Notice that each line is detailing the reliabilities of a subjective well-being measurement that was used in each of them. Look at coefficient alpha for internal reliability. Most of those numbers are high, or close to +1. Interrater reliability wasn't examined because self-report measures were used here. But we can also see that the test-retest reliability scores were relatively high as well. So our conclusion after examining this table is that the subjective well-being score has a very high internal reliability and test-retest reliability based on these 6 studies. Now let's talk some about validity. It's important to note that validity is not the same thing as reliability. They are two separate qualities. While reliability assesses how consistent a measure is, validity assesses whether the operationalization is measuring what it's supposed to measure. We're going to talk more in depth about each of the topics listed here: the measurement validity of abstract constructs, face validity and content validity, criterion validity, convergent validity, and discriminant validity. We'll also discuss in more detail the relationship between reliability and validity. If we think about some other scientific disciplines, such as biology, chemistry, or physics, it might be easy to understand how they are able to use valid measurements. These fields use special tools such as rulers, scales, or thermometers to ensure that they are measuring things like length, width, or temperature reliably. However, in psychology, we are interested in measuring more abstract things like happiness, anger, or self-esteem. So for us, it's really important to make sure we do everything we can to ensure our measurements are as valid as possible. that they're measuring exactly what we want them to be measuring. We can see on this diagram the different types of validity that exist. We've talked in the past about some of these, such as internal validity, and here we're going to focus on construct validity and how we can break that down. I'm first going to talk about the 2 different subjective ways we can assess this, then discuss the 3 different empirical methods. Notice too how reliability, which we talked about before, is necessary but not sufficient for validity. Let's first talk about face validity and content validity. These are both subjective methods to assess content validity. Face validity simply asks if what you're measuring appears to be measuring what you're intending it to. Again, this is simply a first step in assessing validity from a subjective level. Content validity simply asks if your measure contains all of the necessary parts that are laid out in the theory. For example, if a particular theory of personality were to state that personality is made up of both one's thoughts and behaviors, then a personality measure with good content validity would include some measure of both of these things, thoughts and behaviors. While we can use subjective methods to assess validity, most psychological scientists prefer to rely on empirical assessments of validity over subjective ones. One way to empirically assess validity is by examining what's called criterion validity. Criterion validity asks whether the measure is related to a concrete outcome that it should be related to. Let's look at this example. Suppose you work for a company that wants to predict how well job applicants will do as salespeople. Initially, the company uses IQ to predict sales aptitude, shown in the figure on the left here. Then the company develops a sales ability scale to predict sales aptitude, shown in the figure on the right. Aptitude test A, or IQ scores, strongly predict sales performance, so criterion validity is high. Aptitude test B, the sales ability score, on the other hand, does not predict sales as well, so criterion validity here is lower. So this company would probably want to use test A for identifying potential selling ability when selecting new salespeople. Criterion validity is typically represented with correlation coefficients, but it can also be demonstrated with a known groups paradigm, in which you examine whether scores on the measure can distinguish among a set of groups whose behavior is already well understood. For example, the Beck Depression Inventory, or BDI for short, is a 21-item self-report scale with questions about symptoms of depression. In order to test the criterion validity of the BDI, using the known groups paradigm, one could administer the BDI to a group of people with depression and a group of individuals who were not depressed, as determined by 4 psychiatrists who had conducted clinical interviews and provided diagnoses on them. In the graph on the left, you can see that the average BDI scores for the group without depression is lower than the average BDI scores for the group with depression. Thus, BDI appears to have good criterion validity based on the known groups method. Beck also used the known groups paradigm to calibrate scores on the BDI by having psychiatrists categorize participants into the following levels of depression, either none, mild, moderate, or severe. If you look at the graph on the right, you will see that the mean BDI scores for each group increased along with the severity of their level of depression as diagnosed by psychiatrists. Another type of validity is concerned with whether there is a meaningful pattern of similarities and differences. Convergent validity states that a measure should correlate strongly with other measures of the same construct. The figure on the left supports the convergent validity of the BDI with another measure of depression called the CESD, or the Center for Epidemiologic Studies Depression Scale. The 2 measures had a correlation coefficient of R of 0.68, showing that they both correlate strongly and positively with one another. Discriminant validity, also known as divergent validity, states that a measure should correlate less strongly with measures of different constructs. In other words, there must be differences. The figure on the right supports the discriminant validity of the BDI with a score on a physical health measure. The BDI is weakly correlated with physical health and had an R of 0.16. Lastly, let's talk about the relationship between reliability and validity. Remember that just because a measure is reliable doesn't mean it's a valid measure. For example, head circumference and IQ. Remember that reliability is how well a measure correlates with itself. whereas validity is how well a measure is associated with something else. If a measure doesn't even correlate with itself, then how can it be correlated with other variables? So reliability is necessary for validity, but not sufficient in itself. So let's wrap up this week's topics. We talked about some different ways to measure variables, that we could use self-report, observational, or physiological measures, and that there are different scales of measurement with different levels of quantifying variables. We talked about the reliability of measurement. Remember that there are 3 types of reliability: test-retest reliability, interrater reliability, and internal reliability. We also talked about the validity of measurement, how this is different from reliability, and focuses on how the measure is related to other measures. Validity refers to how well something is actually measuring what it's meant to. Finally, we broke down the different ways in which we can measure construct validity, the 2 subjective methods of face and content validity, and the 3 empirical methods of criterion, convergent, and discriminant validity.